Alright, so this slide here was accidentally skipped during lecture. I want to make sure that we talk about it. It should also help you with homework problem number 12 on this week's homework. So we have the relationship between potential energy and conservative forces. So basically here F is some form of a conservative force, and examples of this can be the force from a spring or the gravitational force. And you might remember from earlier in the lecture when we talked about conservative and non-conservative forces, we mentioned that conservative forces have an associated potential energy function associated with them. So there's a very specific relationship between that potential energy function and the conservative force, and that relationship is that the conservative force can be found by taking the derivative, the negative derivative of the potential energy with respect to position. Now, this is in one dimension. In higher dimensions, this derivative becomes a gradient, but we don't need to concern ourselves with that. So basically, the conservative force can be calculated by taking minus du ds. There is also one other form of this equation, the integral form of this equation, which basically tells us that the potential energy is equal to the negative integral of F, so the potential energy between 2 points. So potential energy is often defined with respect to some reference. So if we take a look at the change in potential energy between 2 points, let's say some point 1 and some point 2, well then the integral of f dot ds between these 2 points can give us the change in potential energy. Additionally, let's take a look at this potential energy function that is given to us. And let's say we're looking at some particle that starts from rest in this potential energy function. Well, let's take a look at starting here. What sort of force would this particle feel according to our understanding of the relationship between the force and the potential energy function? Well, first, to calculate what the force looks like, we need to take the derivative of u, which is the potential energy, with respect to whatever spatial coordinate. So du ds, in this case, the spatial coordinate is x, so du ds. Well, that's basically the slope of this function at this point. So f is equal to minus du ds. Well, we see the fact that du ds here is negative because the slope, this is a downward slope at this point. So basically the force is a negative quantity times the minus sign in front, and this basically tells us that the overall force is positive in this case, meaning pointing to the right. So at this point, the force points in the positive x direction because the potential is decreasing in that direction. And the force, according to this formula here, points in the direction that is opposite to the decrease, or it points in the direction of decreasing potential energy, basically. And now let's take a look at a particle that might start at rest on this other end. So let's say we have a particle that starts here. Well, let's take a look at the slope at this point. Well, the slope at this point is positive. So we know du ds is positive. That means f, which is minus negative du ds would be a negative times the derivative here is positive. So the overall force is negative, meaning in the negative x direction, so to the left. So force would act on this particle towards the left at this point. So essentially, a particle that starts at rest here would fall down the potential, and then it'll have enough energy to get over this potential hub, then fall down this potential, reach all the way back to this point. So as this force is doing work on this particle, the potential energy, as the potential energy decreases, is getting converted into kinetic energy. And then when it goes back up the potential, the kinetic energy converts back into potential, because this is a conservative force. There are no losses. So particle that starts at rest here just goes through this potential, makes it to the same point of potential energy here, and then it just oscillates back and forth between these 2 points. All right, so the main takeaways here are that this is a relationship that holds true between conservative forces and some corresponding potential energy function, and the fact that we can, knowing information about the force, we can get the change in potential energy between 2 points by integrating the force between those points.